Welcome back to the AutoML lecture in the age of foundation models. Now we're talking about the next level AutoML by Agentic AI, actually. So we have here again a different kind of shift, and I would call that Agentic AutoML because traditional AutoML systems require manual configuration, rigid data formatting, heavy domain expertise, maybe even to some degree, and that limits their accessibility. And that was one of the bitter lessons, more or less, for AutoML in the last decade. That although we built awesome system with great performance, very efficient, people haven't really always used them. The current large language model agents struggle with end-to-end machine learning complexity, and they rely too heavily on inherent parametric knowledge, leading sometimes to outdated or overly simple code model choices. Lack targeted component-specific debugging maybe even on top. The general idea is we would like to leverage multi-agent architectures to automate perceived data, plan pipeline, generate executable code, and verify and refine solutions iteratively. How we do that is more on core commonalities or core principles we can make use here across different frameworks I will show you in a second. First of all, often we have multi-agent orchestration. So we don't say that we only have one agent taking care of everything, which we may have seen in previous videos. I was saying there was always the one large language model taking care of everything. Now we're saying if you'd like to boil it down to machine learning, we know that there is different kind of parts of our pipeline. So there's maybe a data or perception agent, there's a coder or implementation agent, there's a planning agent, verification agent. So different agents taking care of different kind of things. Furthermore, we have an iterative execution and feedback. That's very common again. Conceptualizing machine learning as engineering as a code optimization problem to find the optimal script given some kind of metric. That's not new. That's as always. And last but not least, we would like to integrate external knowledge. So we know that large language model can hallucinate, but by counting the generation process in retrieved external knowledge rather than relying purely on internal model weights is quite helpful and helps you to get better results. Let's first talk about AutoML Agent. It's retrieval augmented planning. The objective of AutoML Agent was to address complex interdependencies in full pipeline AutoML without the high computational cost of training-based model search. We're using here, very importantly, a retrieval augmented planning system. So it's not a RAG, but a RAP. Funny pun maybe. And which generates multiple diverse end-to-end plans via API calls prior to execution. Then we're adding on top prompting-based plan execution. So it decomposes plans into subtasks, simulates model search using pseudocode analysis without actual execution of that. So it saves us the overhead of that. And then we have the multi-stage verification, so it incorporates strict requests, execution, implementation, verification steps to ensure if it passes everything before that, then we are investing that and it's really going well. Complicated graphic, but let's go step by step through that. So we have a user which is prompting the agent manager. So it's more or less the high-level agent. And that puts a request, and this request will first be verified. If the request is not verified, it goes back, of course, to the agent and then to the user. But let's say the request was fine, what the user wanted. Then there's the prompt agent, is more or less giving a better prompt, for example, a more specific prompt to it, which also leads to the retrieval augmented planning, which then makes use of external sources from Kaggle, from papers with code, from archive, and all of that to get some kind of external knowledge to really kickstart everything from the beginning to really get good solutions. Quite important component, maybe one of the most important ones. So if we now have all of these and we have more the retrieval augmented planning is giving us different kind of plans, so more different kind of pipelines and components. We have the data agent, which is now doing some kind of pseudo data analysis. What kind of retrieval, preprocessing analysis is actually needed. And with that, I forgot that is also then combined with the data and model hub, which gives you more data, for example, to have better analysis and better ranking of models. And the other component is the model agent, which again is doing training free. So that's more still cheap, but it's model search and HPO done based on all the informations we have. Is doing all kinds of profiling HPO, but in a simulated fashion still, right? Then the best things are actually passed to the execution verification. And only if that is really done, we go further to so we get a solution summary. So human could even see what is going on and to a certain degree why. And then the operation agent now gets the full skeleton code. So now we're really going for a full code. That was more here, or only more was all the parts of the plan being figured out. But now we're putting that into the skeleton code, which is maybe defined by the user, maybe also from other agents or further projects. And then the full code and the runtime debugging starts. So the runtime debugging, fairly important, is going over and over again. And with the hope that if there's bug now in the code, it can be fixed automatically. Hopefully at some point that we don't run here an infinite loop or some kind of termination turn. At some point we have a code which is valid. We're going then to the implementation verification. And here, as I said before, we checking again how well it's performing, whether everything is fine, and then hopefully the user can start to deploy the model. So a fairly complex system, but each and every of these idea is not super complex actually. Then there is MLE star, which is doing more targeted and refinement and ensembling actually on top of this very similar idea. So the objective is to overcome a coarse whole script exploration by targeting specific pipeline components for deep refinement. And use ablation studies to find the most impact for a code block. So it's more doing now iteratively updating stuff over and over again, and not with this kind of wrap system from before, but always checking, okay, what could be now the code block I should now next, right? Should I maybe change the optimizer of my neural network, or should I change certain parts of my architecture, whatsoever? And then we find only the extracted block and replace it directly in the script, and thereby getting better and better over time, hopefully. And there's an agentic ensembling, so that goes back to ideas we had before. We were also saying, okay, we have maybe many large language models. Here we're saying we have many agents. They don't do a simple majority voting, but a specialized planner proposes and threads dynamic ensemble strategies. So we can here dynamically decide what kind of agent performs best, and so far, and taking that into account, not only majority voting. So in a sense, multi-arm banded, but on an agent level. I go here a bit more quicker because the main idea is very similar to what we have seen now. So we have more the retriever, we search for tools and task descriptions, retrieve information about the model and code. Then we have all of that. We're doing more or less a first short evaluation on these to get validation scores, and seeing what performs well how, and then trying to find overall an initial solution which performs best. Then we going from there and doing now the ablation part. So what component impacts the most? We modify that. We're seeing how well it performs, getting some feedback on that, and can continue with that. Then we have how the code block refinement itself works. So we have the planner, we suggest a plan, K here, for example, it's implemented, it's doing the evaluation, it's replaced, and so on. It's not super complicated in that sense, right? The most important thing here really about these kind of approaches, these kind of ablation, asking what is most promising and going from there. Then there's ML0, so it's more as a cognitive perception and dual memory idea. So the idea or the objective of that is to achieve zero human intervention across diverse raw multimodal data, which is very ambitious, I believe. And by doing that, what I call cognitive perception, so the automatically extracts perceptual context in library choices and tries to memorize in a structured way, semantically, for example, library documentation to searchable knowledge, so knowledge graphs, or episodic memory, so where we have chronological execution logs and others to provide targeted debugging context. So all of that was, I think the main question behind is how I can structure all this knowledge I extracting and providing anyway, and then doing iterative code improvement with this kind of structured memories we have then. Overall, the summary of these ideas, it's quite important that we here think about modularity, and the modularity in the sense of how machine learning is actually done. So we don't do everything at once, not monolithically, but try to see what are subcomponents, how we can improve subcomponents step by step or with multiple agents and so on. Then we have this kind of grounding. We try to get data from external sources or even have knowledge graphs and all of that. And based on that, maybe feedback-driven refinement, maybe step by step trying to get better and better solutions over time. So I hope this, what we previously discussed, was more the algorithm design perspective, now boiling down again to machine learning, to automated machine learning, you have better insights. And you know how we can now leverage multi-agent AutoML system or agentic AutoML system better for finding novel solutions. With that, I hope to see you in the upcoming videos.